Have you ever just stopped and looked around and really wondered what everything is made of? I mean, really made of? Today, we're going to dig into one of the biggest questions you can ask. What is our world, the universe, and even us? What are we all made of at the most basic level? Let's dive in. I mean, just think about it. The phone or computer you're using right now, the air you're breathing, it's all made of something. For centuries, this question has been on the minds of the smartest people on the planet. What is the fundamental stuff that makes up, well, everything? Well, the answer is actually pretty elegant. You can think of it like a cosmic alphabet, a set of fundamental building blocks that combine in almost endless ways to, literally, write the story of our universe. So the most basic letter in this alphabet, kind of like the letter A, is the atom. For a long, long time, we thought atoms were the end of the line, the smallest things possible. But it turns out they're made of even smaller bits and pieces. Right in the middle, in the nucleus, you've got these positively charged protons and neutral neutrons just hanging out. And zipping around them are these tiny negatively charged electrons. That's it. That simple setup is the foundation for everything you see.
Okay, so what makes an atom of gold different from an atom of oxygen? You'd think it would be super complicated, right? But it's not. It all comes down to just one thing, the number of protons. That's the secret sauce. If an atom has one proton, it's always hydrogen. If it has 8, it's always oxygen. That number, the atomic number, is its ID card. It's really that simple and that powerful. So by the 1800s, scientists had discovered around 60 of these elemental letters, but it was a complete mess, just a jumbled list of ingredients with no recipe. The huge question was, is there a hidden order here? Is there a grammar to this cosmic language? Well, one guy was determined to figure it out. And that guy was the Russian chemist Dmitry Mendeleev. He looked at that chaotic list and saw something that nobody else did, a pattern. He realized that if you arrange the elements in a certain way, their properties started repeating themselves in this really predictable rhythm. It was a massive clue that there was a deeper structure to the universe.
His method was actually pretty simple, but totally brilliant. He wrote down everything he knew about each element on a separate card, and then he started arranging them, kind of like he was playing a game of cosmic solitaire. But here's the kicker. This is the really genius part. When the pattern he was seeing needed a space, he just left a gap. He guessed that these were for elements that we just hadn't found yet, and then he did something incredibly bold. He predicted what those missing elements would be like. And you know what? He was right. Take this one example. He predicted an element he called Eka aluminum. Years later, scientists discovered gallium, and when they compared it to his notes, it was stunning. His predictions for its weight, its density, its melting point, they were practically spot on. This wasn't just a lucky guess. This was proof that the order he had found was real. So Mendeleev's breakthrough gave us the foundation for the modern periodic table. Yeah, the one you remember from high school chemistry. Today, it organizes all 118 known elements, all arranged by that crucial proton count. Elements in the same column act like family members. They share similar properties. It really is the official grammar book for the language of the universe. But there's always a twist, right? It turns out not all atoms of the same element are perfect twins. You can have these variations called isotopes. They have the same number of protons, so an oxygen atom is still an oxygen atom, but they have a different number of neutrons. This just changes their weight a bit, and for some elements, it makes them unstable or radioactive. And that little instability, well, that turns out to be incredibly useful. Why is it useful? Because these unstable isotopes, they act like tiny perfect clocks. They actually give us a way to tell time on a massive planetary scale. They let us read the history that's been written right into the rocks of our own planet. But hold on, how is that even possible? How can a single atom, something so small you can't even imagine it, act as a clock that's been ticking for billions of years? Well, it's all because of a process called radioactive dating. See, these unstable isotopes, they break down or decay into other, more stable elements at a rate that is incredibly, incredibly precise and predictable. It's just like the universe's most perfect hourglass. So by measuring how much of the original parent isotope is left compared to the new daughter element, scientists can calculate exactly how long that atomic clock has been running. And by using this method on the oldest things we can get our hands on, we're talking ancient rocks and meteorites, we have figured out the age of our home planet. And that number, it's just staggering.
It's 4.5 billion years old.
Those elemental clocks have let us build out this entire geologic timescale. It really puts that huge number into perspective. We can pinpoint the first signs of life way back at 3.5 billion years ago, the explosion of complex life around 541 million years ago, the first dinosaurs, and then way, way down at the end of the timeline, our own species shows up. It's a really humbling way to look at our place in the world.
So, we have used this cosmic alphabet to read our planet's deep past. But what about the future? Well, our knowledge of the elements is now the absolute key to writing our next chapter and to tackling some of the biggest challenges we've ever faced.
When we're talking about huge environmental challenges, our playbook usually has two main strategies. The first is mitigation. That's all about trying to reduce or prevent the causes of the problem in the first place. Think developing clean energy. The second is adaptation. That's about finding ways to cope with the changes that are already happening or that we can't avoid. And both of these strategies, they rely entirely on engineering solutions that are grounded in how elements work. And this is where it all comes together. Engineering a better future is elemental science. You want to create more efficient solar panels? You have to be a master of silicon. Building better batteries for electric cars? That's a huge challenge, all centered on lithium. And developing lighter, stronger, more sustainable materials for everything else? That means you've got to know your carbon. Our mastery of this cosmic alphabet is what powers all of this innovation.
So, when you boil it all down, the elements are the letters, the periodic table is the grammar, and together they make up the language of the entire universe. It's a language we've learned to read to uncover our planet's incredible past, and it's a language we're now using to write our future. The only question left is, what story will we choose to write next?